Hello, Gem Hunter. Did you know there are thousands of diamonds scattered across the soil of our planet? Each one has unique colors, inclusions, shapes, and sizes due to its formation process deep within Earth's crust. But among all these variations, there's one type of diamond that stands out, a stone so mysterious that its origin challenges human understanding. Scientists believe this diamond may have been born far beyond our planet, forged in space under extreme pressure and temperature that could only occur during cosmic events like the explosion of supernovae. These diamonds are believed to have traveled to Earth inside meteorites, surviving their fiery descent through the atmosphere before settling into the ground we walk on today. I'm talking about the enigmatic black diamond, a gemstone that not only rivals regular diamonds in hardness, but is so rare that finding one with the right size and quality for cutting, like this one, could completely change your financial life. But first, we need to know some key facts like, what gives a diamond its black color? How did meteorites manage to bring them all the way here from space? And since there are other black gems like black tourmaline and onyx, how can you tell them apart from true black diamonds? And more importantly, how can you find these diamonds in your region? That's exactly what this video is here to show you. Instead of writing a book, we've created a direct and visual explanation because the real answer to these questions is far more fascinating than it seems, especially when you realize that no other diamond color carries as much mystery as the black one. The name itself is so captivating that countless brands and companies around the world use it. Once considered undesirable, the black diamond has now become one of the most elegant and sought-after gemstones in high-end jewelry. In the past, however, it was largely undervalued and ignored by the market. That changed when an impressive 67.5 carat specimen was discovered, belonging to Russian royalty. This legendary stone became known as the Black Orlov, or Eye of Brahma, and it completely transformed the reputation of this mysterious gem. Today, the world of jewelry has surrendered to its allure. Its singular beauty and captivating mystery are finally recognized, granting the black diamond its rightful place among the rarest and most extraordinary gems ever found, and perhaps the only ones that truly came from the stars. So what exactly are black diamonds, and what gives them that deep, mysterious color? A black diamond, also known as cabodanau, is a rare variety of diamond that many scientists believe is even older than regular white diamonds. In fact, some studies suggest it may have formed billions of years ago, possibly outside Earth, before arriving here inside meteorites. There are three main kinds of black diamonds: natural, treated, and man-made. All of them are technically real diamonds, but the differences between them are huge, especially in how they're made and how valuable they are. So if you ever plan to buy a black diamond, it's important to know which type you're looking at. Natural black diamonds are very different from ordinary colored ones. In simple terms, they're a mix of diamond, graphite, and other forms of carbon packed together. While most colored diamonds get their color from trace elements, like boron for blue or nitrogen for yellow, black diamonds get theirs from a heavy concentration of graphite inclusions. These tiny dark particles are so dense that they block almost all light, giving the gem its opaque, jet black appearance that sets it apart from every other kind of diamond. Artificial black diamonds, on the other hand, follow a different path. Lab-grown black diamonds are created using advanced machines that copy the extreme heat and pressure found deep inside Earth. Treated diamonds start out as regular or brownish stones that are later heated or irradiated to turn black. Both are real diamonds, but the treated ones are much cheaper, while lab-grown ones can still be pricey because of the technology used to make them. For comparison, natural blue and pink diamonds are among the rarest and most valuable gemstones in the world, sometimes selling for tens or even hundreds of thousands of dollars per carat. Natural brown and black diamonds, on the other hand, are more affordable, often ranging between $2,000 and $3,000 per carat. The color of black diamonds comes mainly from the graphite and other minerals trapped inside. Because the inclusions absorb light instead of reflecting it, these stones don't sparkle like clear or colorful diamonds. Instead, they have a dark, metallic shine, a kind of subtle glow that looks almost like polished volcanic glass. Scientists think this unique structure might explain why black diamonds are even tougher than regular ones. Unlike colorless diamonds, which are made from one single crystal, black diamonds are formed from many tiny crystals fused together at random. This polycrystalline structure makes them resistant to cracks and almost impossible to break cleanly. Interestingly, before they became popular in jewelry, black diamonds were mostly used for industrial purposes, especially in drills and cutting tools, because of their incredible hardness. Now that we understand what black diamonds are, it's time to uncover the most fascinating part of their story, how these mysterious stones could have traveled all the way from space to Earth. The idea might sound like science fiction, but the evidence supporting it is surprisingly strong. When stars much larger than our sun reach the end of their lives, they explode in massive cosmic events called supernovae. These explosions release unimaginable amounts of heat and pressure, the same conditions needed to form diamonds. In deep space, carbon atoms floating in vast clouds of interstellar dust can be compressed by these explosions, forming tiny diamond crystals known as space diamonds. Over billions of years, this cosmic dust begins to cluster together, forming asteroids and meteorites. Some of those meteorites, scientists believe, were packed with carbon-rich material, a mixture of graphite and tiny diamond crystals that would later become what we know today as cabodanau, or natural black diamond. When these meteorites collided with early Earth, fragments survived the fiery descent and scattered across the surface, carrying with them traces of a distant stellar past. Unlike regular diamonds, which form deep within Earth's mantle and are brought to the surface by volcanic eruptions through kimberlite pipes, black diamonds are never found in volcanic rock. Instead, they're discovered in sedimentary deposits mixed with gravel and river sediments, exactly what you'd expect if they had fallen from the sky and slowly settled into the ground over time. The scientific evidence for their extraterrestrial origin is remarkable. When researchers analyzed the carbon isotopes in black diamonds, they found that the ratio doesn't match anything found in Earth's mantle. It's much lighter, identical to the kind of carbon seen in space dust and meteorites. Even more convincing, some black diamonds contain noble gases like helium and neon, with chemical signatures that perfectly match those found in certain meteorites. These gases could only have been trapped in the stone in an environment outside our planet. Their infrared spectra also tell the same story. Black diamonds share nearly identical absorption peaks with microscopic diamonds found inside meteorites that have fallen to Earth. Those peaks correspond to high concentrations of nitrogen and hydrogen, elements commonly found in interstellar dust clouds. But how exactly did these stones make the journey from deep space to our planet? One theory says they were formed inside a giant cloud of carbon-rich dust somewhere in the galaxy. Over millions of years, gravity pulled parts of that cloud together into asteroids, some of which collided with Earth more than 2 billion years ago, delivering black diamonds into our planet's surface layers. Another theory, just as fascinating, suggests that when a massive meteorite struck the young Earth, the enormous energy of impact instantly transformed carbon-rich surface materials into black diamonds. In this scenario, the meteor didn't bring the diamonds. It created them here on Earth in a single instant of unimaginable pressure. Still, not all scientists agree. Studies comparing black diamonds with extraterrestrial diamonds found in meteorites show nearly identical chemical patterns, including traces of uranium, thorium, nitrogen, and hydrogen, elements linked to high radiation environments that don't exist inside our planet. These results strengthen the theory that at least some black diamonds were born in space, possibly more than 3 billion years ago. To put that in perspective, these stones are older than the continents themselves. While most gemstones tell the story of Earth's geological past, black diamonds may hold the memory of stars that died before our planet even existed. That's why they're often called fragments of the universe. Interestingly, some of the largest black diamonds ever found seem to support this theory. The famous Sergio diamond, discovered in Brazil in 1895, weighed an incredible 3,167 carats, making it the largest rough diamond ever recorded. And it was a carbonado. Its dark, porous texture matched perfectly with other meteorite origin stones. Imagine holding one of those in your hand. A gemstone older than the oceans, older than mountains, older even than life. That's why, among all diamonds, the black diamond remains the most mysterious of all. So how much is a black diamond actually worth? Its price can vary a lot depending on a few key factors like weight, clarity, and overall quality. For example, a small black diamond weighing about 0.11 carats might cost around 33 euros, while one that weighs 0.14 carats could be priced closer to 42 euros. A slightly larger 0.56 carat stone can reach around 168 euros. These are average market prices, which usually include taxes but not shipping or certification costs. In the US market, values can vary even more depending on the origin and quality. Natural, untreated black diamonds are often priced higher than treated or lab-grown ones. Some jewelry-grade natural black diamonds can reach between $2,000 and $3,000 per carat, while treated ones may sell for just a fraction of that. To correctly identify a genuine black diamond, there are a few key signs to look for. Clarity and cut are important, but so are density and mass, which usually range from 3.15 to 3.48. Black diamonds are among the hardest materials on Earth, scoring 10 on the Mohs hardness scale, and are made entirely of crystallized carbon. Their most recognizable features are their porous texture, opaque color, and lack of sparkle or rainbow reflections. These characteristics help you easily tell them apart from other black gemstones like onyx, spinel, or obsidian. Because black diamonds are polycrystalline, their internal structure is very different from other diamonds. Instead of forming as a single solid crystal, they are made up of thousands of tiny crystals tightly fused together. This gives them uneven surfaces, small cavities, and sometimes even tiny gas bubbles trapped inside, features that make them extremely tough, yet unpredictable to cut or polish. Cabodanau diamonds, the most famous natural black diamonds, are mainly found in alluvial deposits in the Central African Republic and Brazil. They were first discovered by Brazilian miners in the 1800s, who named them carbonados because they looked like pieces of charcoal. By the 1860s, these stones were being used in mining and drilling tools thanks to their unmatched hardness and durability. Another unique feature is their faint luminescence, which can sometimes appear as a greenish or bluish glow under certain types of light. Scientists believe this glow is caused by nitrogen atoms in tiny empty spaces inside the stone structure. Some studies even show that radioactive elements could have played a role in their formation. And of course, if you'd like to keep learning about discoveries like this, make sure to like this video and subscribe to our channel so YouTube keeps recommending more gem hunting content for you. Now let's get back to what really matters. Now that you know how black diamonds may have come from space and why they're so different from regular diamonds, we need to clear up one of the most important questions for any gem hunter. How do you know if that dark stone in your hand is a real black diamond or just another common black gemstone? Because here's the truth. In nature and in jewelry, most of the black stones you'll see are not black diamonds. They might be black tourmaline, onyx, obsidian, spinel, hematite, or even treated stones that were made to look darker on purpose. Many of them are beautiful and valuable in their own way, but none of them have the same story, structure, or resistance as a true black diamond. Let's start with something simple. The surface. A natural black diamond, especially carbonado, rarely looks perfect. It usually has a slightly rough, grainy, or pitted texture, sometimes with tiny holes or an uneven skin that reminds you of charcoal or volcanic rock. It doesn't look like a polished glass bead. Stones like black onyx and black tourmaline, on the other hand, often have a smoother, more uniform surface with clean lines, stripes, or a waxy shine. If your black stone looks too perfect, too flat, and too soft in its reflection, there's a good chance it's not a natural black diamond. Next, think about the sparkle. White and colored diamonds are famous for their fire and brilliance, but black diamonds behave differently. Because of all the inclusions inside, they do not show rainbow flashes. Instead, they reflect light in a subtle, metallic way, almost like a polished metal surface. Onyx, glass, and synthetic materials often show a smooth mirror-like reflection. And some imitations may even show colorful flashes that feel too bright for a black stone. Now let's talk about weight and toughness, two details that anyone can notice with a bit of practice. Diamonds are very dense. When you hold a real black diamond of the same size as another black stone, the diamond will usually feel heavier in the hand. Carbonado in particular feels compact and solid, even when its surface looks irregular. Obsidian and glass are much lighter and, more importantly, much easier to damage. If a stone chips, cracks, or scratches easily, it is not a black diamond. That leads to one of the most well-known properties: hardness. Diamonds sit at the top of the Mohs scale with hardness 10. They can scratch almost any other natural material. Black onyx, tourmaline, and obsidian are much softer. This doesn't mean you should take a knife or another stone and start scratching your gem aggressively. That's a quick way to damage something valuable. But in controlled tests done by professionals, a real black diamond can leave a mark on quartz, glass, or steel without being scratched in return. If your diamond gets scratched easily, it is not the real thing. Another strong clue is transparency. True black diamonds are usually completely opaque or nearly opaque, but under a strong light you might still see tiny internal reflections or very small bright points deep inside the stone. Onyx and many synthetic stones, when placed under a strong light, often show a more even color with no internal reflections at all, or they may let a little uniform light pass through the edges. Tourmaline can sometimes show faint transparency along thin edges, something you won't see in a dense natural carbonado. Under a loupe or microscope, the differences become even clearer. A natural black diamond tends to show a chaotic internal structure, with many tiny crystals fused together, microfractures, and irregular patterns. It does not have the smooth, layered bands of onyx or the glassy, uniform look of obsidian. Moissanite, which is sometimes sold as a diamond alternative, usually shows very sharp, symmetrical facets and a stronger brilliance that looks different from the muted, metallic reflection of a black diamond. Cubic zirconia and glass often reveal bubbles, mold lines, or an artificial look that gives them away immediately. If you are examining a stone in jewelry, context and price also tell a story. Real natural black diamonds are rare and do not appear in large sizes at very low prices. If a ring is advertised as a natural black diamond, but costs less than many simple silver pieces, it is probably made with treated stones, onyx, or synthetic materials. There is nothing wrong with that for fashion jewelry, but it should never be sold as a rare cosmic diamond. Professional tools can help too. Many jewelers use thermal conductivity testers that identify diamonds by how quickly they conduct heat. Real diamonds, including black ones, usually pass this test. Moissanite can sometimes behave in a similar way, which is why serious labs also check other properties such as specific gravity, spectroscopy, and the stone's internal structure. For a gem hunter or beginner, the key message is simple: use your eyes. Now let me ask you something. Have you ever seen this type of gravel in a river near where you live? If the answer is yes, then pay close attention, because there's a real possibility you could find diamonds on the ground right in your area. But don't get me wrong, the purpose of this channel is to inspire you to develop this incredible and therapeutic hobby that gets you outdoors and in touch with nature. As I've said before, diamonds are hard to find, but this kind of knowledge could change your financial life forever if you discover just one quality diamond in the wild. And remember, while the best diamonds are still found in underground mines, many valuable ones are hidden in plain sight, right on the ground. And now you may be asking yourself, but how am I supposed to find a diamond in a river? Well, let me show you. Look at this rock here. This is the famous kimberlite rock. If you find one of these rocks in your area, there's a good chance you'll find diamonds nearby. These kimberlite rocks are nothing more than lava that comes from the Earth's mantle through volcanic eruptions. In this process, the diamonds that are formed in this region end up being brought along with this lava, which when it cools ends up trapping the diamonds inside. However, over the course of thousands of years, the forces of nature end up fragmenting some of the kimberlitic rocks, releasing the diamonds trapped inside. The diamonds are carried by the wind, torrential rains, and downpours to the rivers, where they are deposited in the riverbeds or even on the beach. In the same way, diamonds that have been detached from a kimberlite by erosion and fallen into the riverbed can be carried to the beach by the current of the water. But what about diamonds found in rivers? Well, that's where you're going to need those sieves I mentioned earlier. You're going to find a clean spot with no rocks around, Then you're going to dig up the earth a bit to remove the gravel from the alluvial deposits, and you're going to start sifting the material. Start with the largest sieve and work your way down to the smallest, always keeping the smallest sieve under the largest so that the material that passes through the mesh of the largest sieve is caught in the smallest sieves. If you can get 5 or 6 degrees of screen, that would be even better. But let's assume for the moment that you're in an actual river with flowing water. Diamonds found in underground mines have a hexagonal shape with 6 sides like this. However, diamonds found in alluvial deposits, whether in dry rivers or flowing rivers, are rounder than diamonds taken directly from kimberlites. Diamonds found in rivers look like a semi-polished stone. Despite being the hardest mineral on Earth, they also suffer from the effects of thousands of years of wear and tear from friction with the other stones in the river. But then you may ask yourself, how can I tell a diamond from other common stones? It's easier than it sounds. There is one characteristic that only diamonds have, and that is their metallic luster. Take a look at the difference in luster between a rough diamond and other common stones. Can you see how metallic a diamond's luster is? I'm sure that if you find a diamond after watching this video, you will have no doubts. Of course, you'll need to do further tests to certify the diamond, but learning to look closely at the metallic luster of diamonds is more than enough. It may be hard to notice at first, but over time, by watching the videos here on the channel, you'll become familiar with the metallic luster of diamonds. If you look at a diamond from a distance, it will look like a piece of polished iron, not a stone. So if you notice something glittering in the gravel of the alluvial deposits, it's a good idea to start sifting. If you're lucky enough to find a diamond, it's likely to be quite small, so try finer sieves if possible. Another important factor now is the minerals that are indicators that there are diamonds in the river that I mentioned at the beginning of the video, because not every river is going to have diamonds. But how do you know if the river you're looking for has diamonds in it? In rivers that have diamonds, you'll find some minerals that are indicators of diamonds, which are mainly garnet, chromite, and ilmenite. In previous videos, I've talked about all the indicator minerals, but these 3 minerals are enough. Garnet, for example, is a gemstone that is much more common and cheaper than diamonds and is sometimes confused with rubies. However, there are some differences. The most common type found in rivers is parope garnet, which has a reddish, dark color, sometimes grayish. And you usually find them like this in rivers, in rounded cubic shapes, with several sides, sometimes semi-polished. Like rubies and diamonds, they are quite heavy compared to ordinary stones of the same size, some of which, when clear, are beautifully cut and can be worth a lot of money. But what is important here is that you recognize and find these stones. Because garnets are formed in volcanic rocks under conditions similar to those of diamonds, they can indicate that diamonds are present in the area, just like ilmenite. This is basically an oxide of iron and titanium. This mineral is black with a metallic luster. Its shape is trigonal and it can have some facets. It looks like a piece of raw iron, is very heavy, has a hardness of about 6 on the Mohs scale, and is a strong indication that diamonds may be present. Some emenites can even be mistaken for black diamonds at first glance. The third important indicator is chromite. This is also a type of iron oxide that contains iron and chromium and other combinations of minerals. It has a darker metallic appearance, but is more irregularly shaped, more rustic than ilmenite. They are also very heavy, much heavier than other stones of the same size. It will feel like a small piece of lead in the palm of your hand.
Are dunite, which is this one, and chromite, which is this one. Now they're very similar in colour. The dunite is exceptionally fresh here, and so is a greeny black kind of colour, whereas the chromite is more of a black.
Finding chromite in rivers is also a strong indication of the presence of diamonds, as well as sapphires and rubies. That's it. You found these minerals, but how do you get the diamonds out of the river? In a practical way? Well, you put some river gravel in the sieve and then you make circular movements, turning the sieve, because diamonds are heavy, more so than other stones, and they'll end up at the bottom of the gravel, along with garnets and ilmenites and chromites, if there are any, including gold, if there's any in the river. With circular movements, the heavier minerals will concentrate in the middle, and then you just have to do this process from the coarsest screen to the finest, just as I told you at the beginning of the video. At the end, just spread out the gravel from the sieve and look carefully, because now you're going to have to see the diamond with your eyes. But how do you do it? Diamonds don't have the same luster as ordinary quartz crystals, so don't be fooled by transparent stones. Look for the metallic sheen I showed you earlier. It will certainly catch your eye from a distance. Diamonds are very small, so keep your eyes open to make sure you don't miss them. Don't be fooled by big stones. And when I say big, I mean over a gram, which is pretty big for a diamond. One more important point, when you find your first diamond, remember that it can't always be a quality stone. There are darker colored diamonds that have a lower value and others full of inclusions that will only serve as industrial diamonds. But even if you find a low-quality diamond, it's already a reason to rejoice because you're on the right track. The place has real diamonds, and it's worth looking for more. Even if diamonds are not easy to find, it doesn't hurt to try. You never know when your lucky day will come, do you? But before you rush out to start searching for rocks that could be worth a fortune, there's one last thing you need to know. A lot of people out there do find stones with serious value, but because they don't know how to properly identify the mineral type, they either ignore it or worse, sell it for a fraction of what it's really worth. Unfortunately, this happens all the time. Valuable minerals and even gemstones being sold for ridiculous prices, simply because the person holding them didn't recognize what they had. That's exactly why I created the book, Gemology Journey for Beginners. A complete, straightforward, and practical guide made for anyone who wants to learn how to identify the most common types of gems and minerals, even without professional tools. Inside, you'll learn how to perform simple tests for hardness, density, texture, and luster using everyday tools. With this knowledge, you won't need to rely on anyone else's opinion to know what you found. You'll be able to analyze your discoveries with confidence and maybe even turn this skill into a side income or long-term investment. And if your goal isn't to sell, no problem. The book also includes an exclusive collector's chart listing some of the world's most valuable minerals, their characteristics, rarity levels, and practical tips to organize your finds as your collection grows. Now, if you're still taking your first steps or just not ready to grab the book yet, that's perfectly fine. You can subscribe for free right here on the channel and keep following our videos to keep learning how to identify rocks with critical metals, which are now the new gold of the tech industry. We all know there are many rare and valuable gemstones around the world, like rubies and diamonds. But what if I told you that an ugly, imperfect rock could be worth just as much as a diamond? Would you believe it? Take a look at this stone when it's cut in half. Notice the intricate patterns hidden inside it. That's the secret beauty locked within meteorites. That's right, some of them even look like gold. But why are these stones so valuable? The answer lies in what they carry: priceless information about outer space. To give you an idea, if you tried to collect the same meteor that landed in someone's backyard by launching a rocket into space, that mission would cost billions of dollars. But because these rocks literally fall from the sky, ordinary people, with a bit of luck, can find one and make a small fortune. And you could be one of them if you know how to look. So in today's video, we're going to explore what meteorites are, how they form, their key characteristics, and most importantly, how you can identify one if you ever find it. We'll also look at some of the most famous meteorite falls in the United States and discover why these rocks can be worth millions. So what exactly are meteorites? In simple terms, meteorites are fragments of solid bodies from space, pieces of asteroids, planets, or moons, that survived the violent entry through Earth's atmosphere. Each meteorite is a physical sample of the distant past of our solar system, a natural time capsule holding information about the earliest stages of planetary formation. These fragments originate from extremely energetic cosmic processes. When two asteroids collide, for example, part of their material is ejected into space at tremendous speed. Over time, the gravity of nearby planets, such as Mars or even Earth, can capture these fragments and pull them toward the surface. In other cases, meteorites are produced by giant impacts on planetary bodies, like the Moon or Mars, which blast rock material into space. Those pieces can travel for millions of years before finally crossing Earth's orbit. Most meteorites discovered so far come from the asteroid belt, a vast region located between Mars and Jupiter, filled with billions of rocky and metallic bodies of various sizes. Collisions there are common, constantly generating debris that occasionally escapes the main belt and drifts into unstable orbits. Some of these fragments are deflected toward the Sun and eventually cross paths with Earth. But not all meteorites come from the asteroid belt. Isotopic studies conducted at institutions such as NASA's Johnson Space Center and the University of Arizona's Mineralogical Institute have shown that a small percentage of meteorites are actually of Martian or lunar origin. This was confirmed by analyzing gases trapped inside the samples, gases identical to those in the atmospheres of Mars and the Moon. These meteorites are extremely rare and highly valuable, both scientifically and commercially, as they represent authentic material from other worlds. From a chemical and mineralogical standpoint, meteorites fall into three major categories: stony, iron, and stony iron types. The stony meteorites, known as chondrites and achondrites, are the most common. Chondrites contain tiny mineral spheres called chondrules, which formed at the very beginning of the solar system about 4.56 billion years ago, even before Earth existed. These chondrules record the thermal and chemical history of the primordial solar nebula that gave birth to the planets. Achondrites, on the other hand, are more evolved rocks that form through partial melting inside planetary bodies, which is why they closely resemble basaltic rocks found on Earth. The iron meteorites are composed mainly of iron and nickel. They formed in the cores of small planetary bodies, known as planetesimals, that experienced internal differentiation, meaning the separation of heavy metallic material from lighter silicates. When those bodies were destroyed by collisions, their metallic cores fragmented and eventually became meteorites. These often display a metallic sheen and complex crystalline structures known as Widmanstätten patterns, visible when the metal is polished and treated with acid. This pattern is unique to meteorites and cannot be replicated artificially, making it one of the most reliable visual signs of an authentic specimen. Finally, there are the stony iron meteorites, called pallasites. They consist of a metallic matrix embedded with transparent crystals of olivine or peridot. Pallasites are considered the most beautiful of all meteorites, and some slices, when polished, are even used in jewelry. Scientifically, however, they are far more important because they are believed to have formed at the boundary between the metallic core and the rocky mantle of ancient planetary bodies, regions that are completely inaccessible on any planet today. Beyond their composition, the age of meteorites is astonishing. Through radiometric dating methods, such as uranium lead and samarium neodymium isotopic analysis, scientists have determined that most meteorites are between 4.4 and 4.6 billion years old, making them the oldest solid materials known. Some preserve minerals such as forsterite, enstatite, and troilite, which condensed directly from the original solar nebula, the same gas cloud that formed the Sun itself. Another crucial aspect is the role meteorites play in understanding the origins of life. In some carbonaceous chondrites, scientists have identified complex organic molecules, including amino acids and carbon-based compounds that do not naturally form on Earth. These discoveries support the hypothesis that some of the basic building blocks of life may have been delivered by meteorites billions of years ago through a process known as panspermia. So how can you tell if a rock you find is actually a meteorite, a true fragment from space, and not just an ordinary stone from Earth? The process starts with close observation, looking carefully at the rock's appearance, texture, and weight. From there, you can perform a few simple tests at home before turning to professional analysis. Most people imagine a meteorite as a dark, irregular rock, and that's a good starting point. However, there are key differences between a real meteorite and common terrestrial materials like volcanic rocks, slag, or iron ore. Meteorites are divided into three main groups: stony, chondrites, and achondrites, iron, and stony iron, also called pallasites. Each group has distinct physical traits that help in identification. Iron meteorites are the easiest to recognize with the naked eye. They contain very high amounts of iron and nickel. typically 85 to 95% iron, with smaller amounts of nickel, cobalt, phosphorus, and sulfur. This composition makes them extremely dense. While most Earth rocks have a density of 2.5 to 3 grams per cubic centimeter, an iron meteorite can exceed 7.5 grams per cubic centimeter, heavier than solid steel. When cut open, the inside reveals a silvery metallic luster and a distinctive crystalline pattern known as the Widmanstätten structure, formed by the slow cooling of metal inside planetary cores billions of years ago. This pattern is unique to meteorites. It cannot be reproduced artificially. In stony meteorites, the appearance is different. Their surfaces are usually dark and coated by a thin, glossy black layer called the fusion crust, created as the rock burns through Earth's atmosphere. Although it's only a fraction of a millimeter thick, it's one of the most reliable indicators of a genuine meteorite. This crust may show a subtle sheen, small pits, or a melted glassy texture caused by intense heating. Another signature feature is the presence of regmaglyphs, shallow thumbprint-like depressions formed by ablation and turbulence as the meteorite passed through the atmosphere. These aerodynamic marks prove the rock endured extreme heat, something that never occurs in ordinary Earth stones. Specimens that retain well-defined regmaglyphs are especially prized by collectors and researchers. Inside, stony meteorites are typically grayish or greenish, often containing tiny, shiny specks of metal visible under magnification. These metallic grains are made of iron-nickel alloys that resist oxidation. Some types, like chondrites, display small, rounded structures called chondrules, which never appear in terrestrial rocks. Their granular texture and mixture of silicate minerals with metallic inclusions are strong clues of extraterrestrial origin. When it comes to shape, meteorites are rarely symmetrical. Most are irregular, with rounded edges and rough surfaces, a result of partial melting and fragmentation during atmospheric entry. Perfectly spherical or flat meteorites are exceptionally rare. They also lack visible crystals or the glassy brilliance often seen in Earth-formed minerals. A simple magnet test is often the first step. Because of their high iron content, most meteorites react strongly to a neodymium magnet. If the pull is strong, that's a good sign, but not proof. Certain Earth rocks, like magnetite, hematite, or industrial slag, can also be magnetic. The difference is that meteorites are unusually heavy for their size and do not leave a black streak when scraped across unglazed ceramic, while magnetite and hematite do. Another easy check is the fracture test. If you carefully break a small, non-valuable piece, the interior of a meteorite usually shows a uniform structure without visible crystals, sometimes with a metallic shimmer. In contrast, most terrestrial rocks break along granular or glassy surfaces, revealing separate mineral grains. Weight is also a quick indicator. A small 2-inch metallic meteorite can weigh more than a rock the size of an apple. This difference in density is immediately noticeable the moment you hold it. For those who want to search more effectively, portable metal detectors calibrated for iron and nickel can help locate meteorites buried just beneath the surface. Professional hunters also use thermal imaging drones to spot density anomalies in deserts or dry plains, where the dark color of meteorites contrasts sharply against pale soil. A common trap for beginners involves what collectors call meteor wrongs. These are Earth rocks that look like meteorites but aren't, such as industrial slag, basalt fragments, iron concretions, or rusted metal debris. Real meteorites have a thin, even rust layer with a reddish-brown tint, not thick, crumbly oxidation. Their interiors remain metallic and shiny even after centuries of exposure. To confirm authenticity, the next step is to measure exact density. Weigh the sample, then divide by the amount of water it displaces in a graduated container. A result above 4 grams per cubic centimeter is a strong sign of extraterrestrial origin. Additional properties, such as electrical conductivity and nickel content over 5%, are verified through laboratory testing. These observations and simple tests are essential for avoiding mistakes before sending the specimen for professional examination. They are the first real steps in turning curiosity into discovery and perhaps finding a rock that truly came from beyond our planet. After performing all the basic tests at home, the most important step to confirm whether a possible meteorite is genuine is professional scientific identification. This is where specialized institutions come in. Laboratories equipped with advanced analytical instruments capable of determining, with complete accuracy, certainty, whether a specimen is truly extraterrestrial. In the United States, the main reference center is the Smithsonian National Museum of Natural History in Washington, D.C. The museum's Department of Meteorites houses one of the largest collections in the world, with more than 45,000 registered and cataloged samples. There, teams of geologists, astronomers, and chemists specializing in meteorites have developed precise protocols for analysis, preservation, and classification. On the Smithsonian's official website, you can find detailed guides with side-by-side images comparing Earth rocks and genuine meteorites, as well as a flowchart that explains the step-by-step screening process. Researchers outline which characteristics should be checked before sending a sample and which types of rocks are not accepted. This initial screening is crucial because it prevents the submission of clearly terrestrial materials, which represent about 90% of the samples received each year. The Smithsonian also offers a mail-in laboratory analysis service, accessible to anyone in the world. The procedure includes instructions on how to collect, package, and label a sample correctly. The stone should be cleaned without chemicals, wrapped in aluminum foil or plastic film, and shipped with details about the location and date of discovery. This information helps scientists correlate the sample with recent recorded meteor events. After the sample arrives, the team performs an initial visual and magnetic inspection. If the material shows promising characteristics, it proceeds to advanced testing. Among the methods used are scanning electron microscopy, SEM, which reveals the internal microstructure and metallic alloys, X-ray fluorescence spectroscopy, XRF, used to determine elemental composition, and isotopic analysis, which measures ratios of radioactive elements, such as uranium, lead, and neon. This last method is essential for establishing both the meteorite's age and its likely origin, whether from Mars, the Moon, or the asteroid belt. Another technique, X-ray diffraction, identifies the specific minerals present in the sample. This type of analysis can confirm, for instance, whether the rock contains olivine, enstatite, kamacite, or troilite, minerals typical of meteorites but rare in terrestrial rocks. Combining these results produces a unique mineralogical profile, almost like a fingerprint, that allows scientists to classify the meteorite within one of the more than 60 officially recognized subgroups. Beyond the Smithsonian, other U.S. laboratories are also internationally recognized. The UCLA Meteorite Gallery in California maintains a dedicated team for analysis and authentication, and provides a high-resolution image database for comparison with known samples. The Field Museum of Natural History in Chicago also offers scientific consultation and houses mass spectrometry instruments capable of detecting trace volatile elements. Meanwhile, the Lunar and Planetary Institute in Houston collaborates with NASA on meteorite classification and storage programs, particularly those recovered from Antarctica, which are among the best preserved on Earth due to the cold, stable environment. In some U.S. states, local universities also accept public submissions, either free of charge or for a small fee. For example, the University of Arizona conducts preliminary analyses and maintains a public database that records all confirmed meteorite finds in the country. This transparency is valuable because each verified meteorite contributes to the global distribution map and helps researchers trace potential atmospheric entry paths. Another excellent resource is the Meteoritical Bulletin database, an online catalog maintained by the Meteoritical Society that compiles information on every officially recognized meteorite since the 19th century. There you can check whether a new discovery matches a previously recorded fall or represents a completely new composition, something that greatly increases both scientific and commercial value. Experts also provide detailed guidance on how to properly preserve a meteorite after discovery. The key is to store it in a dry, sealed environment, avoiding prolonged contact with humid air since iron and nickel oxidize rapidly. The best practice is to keep the specimen in an airtight plastic container with silica gel packets to control humidity. Never apply oil, varnish, or cleaning products, as these can chemically alter the fusion crust and compromise future analyses. Anyone seeking a formal authenticity certificate can request one from recognized institutions. This document includes the meteorite's chemical composition, official classification, and registry number, confirming its legitimacy for private ownership, sale, or museum donation. As of 2025, the average cost of this service in the United States ranges from $100 to $400, depending on the complexity of the analysis. Now that you know how meteorites form and how to identify them, let's look at some real cases of meteorite falls recorded in the United States, where science and luck met in truly remarkable ways. The U.S. is one of the countries with the largest number of cataloged meteorites in the world, more than 1,800 confirmed discoveries so far, according to the Meteoritical Bulletin database. That number is due not only to the country's vast and geologically diverse territory, but also to its strong culture of research and astronomical observation. Over the past 2 decades, several events have drawn attention from scientists and the media. One of the most fascinating cases is the Sierra del Carmen meteorite, which fell in 2007 along the Texas-Mexico border. The event was captured by dozens of security cameras, and witnesses reported a bright blue flash in the night sky followed by a sonic boom.
That's a meteor! This is so unreal!
Fragments were recovered within hours by researchers from the University of Texas, who confirmed it was an H5 ordinary chondrite, a common type of stony meteorite, but with an exceptionally well-preserved fusion crust. The main specimen, weighing about 14 kilograms, 30 pounds, is now part of the collection at the Texas Memorial Museum in Austin. Another important case is the Norton County meteorite, recovered in Kansas in 2006. The name actually refers to an earlier fall that occurred in 1948, but new fragments were uncovered during agricultural excavations in the same region nearly 60 years later. The material was identified as an obrite, an extremely rare meteorite made almost entirely of enstatite, a pale magnesium silicate. Obrites are thought to originate from asteroidal bodies that form closer to the Sun, and their composition offers valuable clues about the early heating processes in the inner solar system. Only a handful of museums in the world possess samples of this type. In 2003, another notable event took place in Illinois, the Murrayville meteorite. Local residents observed a shower of fragments after a bright fireball crossed the twilight sky. Roughly 30 pieces, totaling just over 10 kilograms, 22 pounds, were recovered from nearby farms. What made this case special was the detailed documentation carried out by amateur astronomers and meteorologists, who calculated the object's atmospheric trajectory with remarkable precision. Their data showed that the meteorite entered the atmosphere at a speed of 16 kilometers per second, about 36,000 miles per hour, an important value for orbital dynamics research. Another interesting case occurred in 2002 near Ainsworth, Nebraska. Although there were no visible flashes reported, a farmer discovered dark, magnetic stones scattered across his property weeks after a thunderstorm. Later analysis confirmed that this was a strewn field, meaning the meteorite broke into dozens of pieces during atmospheric entry. This case became particularly valuable for studying fragment dispersion, helping scientists better understand how meteorites shatter in flight. Today, part of the Ainsworth collection is displayed at the University of Nebraska State Museum. The Murray meteorite, which fell in 2000 in Kentucky, also holds an important place in history. It's classified as a CM2 carbonaceous chondrite, the same type that contains amino acids and complex organic compounds. These meteorites are intensely studied because they preserve chemical material similar to what existed before Earth formed. Samples from the Murray meteorite revealed stable organic molecules, reinforcing the theory that meteorites may have delivered some of the basic building blocks of life to our planet. For that reason, it remains one of the most scientifically significant meteorites ever found in the United States. Beyond these classic cases, new events continue to occur with surprising frequency. In 2012, the Sutter's Mill meteorite in California was witnessed by thousands and recorded by dashboard cameras across the state. It exploded over El Dorado County with an energy release equivalent to 4 kilotons of TNT, about 1/4 the yield of a small nuclear bomb. Fortunately, no one was injured and fragments were collected within hours. Sutter's Mill also belongs to the carbonaceous chondrite group, and its study revealed organic compounds never before detected in meteorites. More recently, in April 2023, residents of Maine reported a loud explosion and saw a brilliant fireball streak across the sky. NASA's weather radar tracked its path and helped recovery teams locate fragments within 48 hours. This was the first officially confirmed meteorite in the state's history. The small fragments, only a few centimeters in size, were classified as H chondrites, and some were later auctioned for over $25,000 each due to their rarity and the well-documented fall. Another widely publicized incident happened in 2020 in Missouri, when a 2-kilogram, 4.4-pound meteorite crashed through the roof of a home in the city of Winterset. The impact was minor, but enough to break through the ceiling. Unaware of its value, the homeowner posted photos online, which quickly drew the attention of experts from the Central Missouri Astronomical Association. After analysis confirmed its authenticity, the meteorite was purchased by a local museum. These cases show that meteorite falls can happen anywhere, and that public awareness and quick observation are crucial for recovery before weathering or erosion destroys them. Today, most new discoveries in the United States are made thanks to automated monitoring systems, such as NASA's All-Sky Fireball Network, which uses cameras across multiple states to track meteor trajectories and predict potential impact zones. Why can meteorites be worth millions? Because they are literal witnesses to the early formation of our solar system, preserving information about the origin and evolution of celestial bodies. These relics, unchanged for about 4.5 billion years, are priceless to scientists who study how everything began. Most meteorites weigh only about 10 grams, roughly the size of a bean, and burn partially as they enter Earth's atmosphere, producing what we know as a shooting star. That bright streak across the night sky isn't a star at all, but a small piece of cosmic rock burning up as it falls toward Earth. Larger meteorites that survive their fiery descent and reach the ground are much rarer, and that's what makes them so valuable. Each recovered fragment is a one-of-a-kind piece of the universe's history. Museums, universities, and private collectors around the world compete to acquire these samples, often paying substantial sums to own a genuine piece of space. But what about you? Have you ever wondered if there might be a meteorite in your area? Take a closer look at the stones around you. One of them might be a cosmic fragment that has waited millions of years to be found. Examine it, test it, compare it, and who knows, the next great discovery might come from your own backyard. And if this topic sparked your curiosity and you'd like to dive deeper into the world of gemstones and valuable minerals, the physical book Gemology Journey for Beginners is available now on Amazon, in the first link in the description. This book brings together, in a clear and practical way, everything you need to start identifying gemstones and recognizing real mineral value, the same methods we use here on the channel. Now that you know everything about meteorites, click on the video appearing on your screen to discover where real diamonds found in rivers actually come from. Thanks for liking and subscribing. Good luck, Gem Hunter.